Hello again, chemistry class. We're back. Now, I have another video for you today, and today we're going to be talking about heat calculations. So I promise that today's video is going to be shorter than the one yesterday, okay? I've only got 5 slides that I want to go through with you, so I promise it's not going to be 36 minutes like it was before. Now, let's first start by looking at a heat curve. And let's actually make this more specific. Let's make this the heat curve for water. So for water, this section down here with the slope, this is when the water is ice, right? And then at 0 degrees Celsius, we see that we have a phase change demonstrated by that horizontal line. And as soon as we get to here, we are going to have liquid water. So the next time we have a phase change is going to be again when we have another horizontal line, and that is at 100 degrees Celsius. And right when we transition all of that mass of water, liquid water, into steam. All right, so this is steam, which we are more commonly going to call as water vapor. So in your notes right now, you guys can either draw a fresh heat curve and label these things on it, or you can take one of the previous heat curves that you've drawn in your notes and you can just kind of add to it with all this stuff so that you can make it a water-specific heat curve. But either way, I want you to have this in your notes because we're going to be adding to this heat curve. We're going to be adding on more information to it. So not just what phase is at each part and what temperature each phase change occurs at, but we want to add some new things. Okay, so well, let's start at the beginning. Let's go with water as it's on its journey from solid to gas. So we'll start with ice. And as we add, if you guys remember, it's not shown on here, but the x-axis on this graph is energy added over time. So we're constantly adding energy into this system. And at the beginning, when we add energy to the system, the temperature is going up. And that's why we see this increasing line, okay, this line that has a positive slope. Now remember, in this section, when we have the phase change, we still are adding energy to the system. However, there is no change in temperature here. So please don't get those two things confused. We are always adding energy to this system, always, always, always. However, we don't always have to have a change in temperature as a result of that. And when that occurs, that's when we have that phase change. Okay, so in this case, we're talking about melting. We were going from the solid to the liquid state, so we were melting. I also want to give one other quantity to this area where we were melting and where we're going from our phase change from solid to liquid. We're going to refer to this during our heat calculations. And we're going to refer to all this energy that's not creating an increase in temperature. It's instead creating a phase change. We're going to call that amount of energy the heat of fusion. So it's a capital H with a small f, and I want you guys to have that in your notes. For right now, know that this is kind of where the heat of fusion is going to be on our heat curve, but in the next couple slides, we're going to go into what exactly that means. We can look again, and we've got another one of those flat areas where a phase change is occurring, and this time we're going from a liquid to a gas. So if you guys remember that, that would be called vaporization. And again, because we're still adding energy, but we are not increasing the temperature, we're going to give that amount of energy a special name, and it's not going to be called the heat of fusion this time. This time, it's going to be called heat of vaporization. and we're going to talk about what heat of vaporization means. And again, what I'm really referring to when I talk about heat of vaporization or heat of fusion, it's the amount of energy that we put into the system during that phase change. And that's going to help us do a whole lot of calculations. All right, I would like to get rid of this recorder. Hold on just a moment. All right. So another thing that you guys have in your notes already is your lovely picture that you drew yesterday of the 3 states of water all in one picture together. And then we drew these really lovely close-up views of both what this water looks like as a solid, what it looks like on the molecular level as a liquid, and what it looks like on the molecular level as a gas. So I would like for you to add to this drawing, and I want you to add that going from a solid to the liquid, that is heat of fusion. The amount of energy that it takes to go from a solid to a liquid is that heat of fusion. And then when we go from a liquid to a gas, this is the heat of vaporization. So this is H sub V. They're heats, so we're talking about energy. It's the energy that it takes for us to go from a liquid to a gas. Again, they don't at all impact the temperature change of our material. That's completely separate. We're only looking at the phase change where we have no change in temperature. That's when we talk about heat of fusion and heat of vaporization. So when we're talking about a quantity of energy, what variable do we use? You guys, I think, already know this. If you reach back in your minds to first semester, we did a whole lot of stuff with heat, okay? If you remember, heat, we used the variable Q to talk about heat. And how much energy does it take to increase the temperature of liquid water? Well, we have to reach back again to first semester and try to think to ourselves, what did heat equal? Well, MC delta T. Does this look familiar? I hope it does, because it's coming back. Okay, we're looping it back around, and we're going to do the heat calculations once again, and we're going to use this same equation. So let's see, do we remember what it all is? So Q, it refers to our quantity of energy. The amount of energy that we've got is always going to go in for Q. What is M? Well, M refers to mass. Lowercase c was that specific heat constant. Much of what we did first semester was trying to figure out what the specific heat was for various materials. You guys did a lab where you found the specific heat of a certain metal. So that specific heat is coming back once more. And then delta T is a little bit more self-explanatory. We're talking about the change in temperature. Okay? What are all the units for these things? That's something else that's good to keep in mind. Well, we remember that energy is going to be measured in joules, okay? Mass is going to be measured in grams. Specific heat, that one's the one that's a little bit tough. That is joules per gram degrees Celsius. And then change in temperature, that's going to be measured in degrees Celsius. So you guys have to keep these units straight. You're going to have units on all of your answers. Anytime you use a number, make sure you have a unit for it. So know what unit goes along with what variable. Okay? Okay, so now here is the math bit. Here are the heat calculation parts. What we're going to do is we're going to look at our general heat curve, and we're going to label the different parts. So when we are heating up our solid phase, we're going to call that part 1. When we are transitioning from solid to liquid. That's going to be stage 2. Stage 3 is when we are a liquid. 4 is when we go from a liquid to a gas. And 5 is when we are a gas. And each different stage is going to cause us to do a little bit of different math. So if we think about stage 1, this is when we are ice, right? If we want to do some heat calculations, we would say that Q is equal to the mass of ice that we have times the specific heat constant of ice times the change in temperature of that ice. And as long as we know 3 of those 4 things, we can calculate the last one. So in problems that you might be receiving this unit, you might know the mass, the specific heat of ice, and the change in temperature. I'm going to ask you how much energy was either put into the system or taken out of the system. I might tell you how much heat was put into the system, the specific heat of the ice, and the change in temperature. I'm going to ask you to tell me what was the mass of the ice that was in there. Okay? For part 2, now we don't have a change in temperature, right? This area is flat. There is no change in temperature. So using Q equals mc delta T isn't going to work for us anymore. That delta T would be 0, and we would say that the heat added to the system is 0. But we know that that's not true. We know that even in this area of the graph, we are adding energy to our system. So we're going to have to use a different tool in order to calculate how much energy there is there. And that tool is going to be that the heat is equal to the mass of ice turning into water or water turning into ice times the heat of fusion. So heat of fusion is a number. It's something that people have experimentally derived over the years. Usually you'll be able to look it up in a table. That's most classically how you would get that information for heat of fusion, is being able to look it up in a table. However, in the practice problems that you may get, you might be given the mass and the heat of fusion, and I'm going to ask you how much energy there was dumped into the system, or I might tell you how much energy we dumped into the system. I'll tell you the mass, and I'm going to ask you to give me what the heat of fusion for that material is going to be. So as long as we know 2 of the 3 things, we can solve this equation. Now that we're in stage 3, we're going back to an area that has a temperature change. And since we have a temperature change, we can go back to our good old friend Q is equal to mc. And this time I'm not going to use the specific heat of ice because now I'm in my water phase. So I'm going to use the specific heat of, actually I'm going to be more specific. Instead of just saying water, I'm going to say liquid water. Because let's face it, this is all water, no matter what. It just might be solid water, liquid water, or water vapor. Okay, so it's my specific heat of liquid water times the change in temperature. And we would be able to use this just like how we did in stage 1 when we had ice, and it's going to look a lot like the stuff that you guys did first semester. So area 4, back to flat. It should be no surprise to you guys here that in area 4 then, our heat is going to equal the mass, and rather than the heat of fusion, since we're going from water to gas, we're going to use the heat of vaporization. And heat of vaporization, very similar to heat of fusion. Most classically, you would be able to look it up in some kind of a table for that particular material. In practice problems, I may give you that value and the mass, ask you for the heat, any of that kind of stuff. Again, as long as we know 2 of these 3 variables, we can solve this equation. And then the last one here, we are a gas. And so, in order to figure out anything about heat, we would use mass times the specific heat, and this time we would use water vapor times that delta T. I hope that you guys see a pattern in these equations, not just in color, but the fact that the three equations that are in red are all very similar to one another. The only thing that's changing is the specific heat, really. And the ones that are in green, hopefully you see that those are really similar to one another. The only thing that's changing is whether or not you use heat of vaporization or heat of fusion. So I'm not asking you guys to memorize 5 equations, but I am going to ask you to know how to use 2 different equations and be able to understand when you need to use MC delta T and when you need to use M times H. Okay? I think that we can do it. So let's look at maybe what a problem would look like. What quantity of heat is required to raise the temperature of 450 grams of water from 15 degrees Celsius to 85 degrees Celsius? So let's try to identify what this problem is telling us right away. So we want to know what quantity of heat. So we want to know what Q is going to be. Q is equal to question mark. We're going to raise the temperature of 450 grams of water, so we know the mass is 450 grams. And we are going from 15 degrees Celsius, so that's our initial temperature, to 85 degrees Celsius. That's going to be our final temperature. So delta T, what is delta T going to be? So delta T, well, if we think about it, it is really just the final temperature minus the initial temperature. So for our case, it would be 85 degrees Celsius minus 15 degrees Celsius. So it should be 70 degrees Celsius. And now I want you to ask yourselves, is it okay to have a negative delta T? Is it okay that my initial temperature is bigger than my final temperature? Yeah, we can have that, right? If heat is leaving our system, so let's say that our system is just a bunch of liquid water. If we had heat leave that system, the temperature would go down and our liquid water might become ice. And that's okay. So what does that mean? So negative delta T means that heat is leaving. Now you have to be able to determine, should I have heat leaving or should I have heat coming in? Should my temperature be going up because heat is coming in, or should my temperature be going down because some heat is leaving? That's something that you need to read out of this problem. So for our problem, since our temperature is rising, heat is coming into the system, and we would expect that our delta T should be positive. So other things that we need to know in order to solve this problem. Do we know the specific heat of liquid water? It's not given to us in the problem, right? I don't see it anywhere in that sentence. But again, this is kind of a review of what we did first semester. You guys remember first semester that I asked you to memorize the specific heat of water. It was not going to be given to you. So you guys should already know, hopefully it stayed in your brain over the many months that it has been since first semester. But the specific heat of water is 4.184 joules per gram degree Celsius. All right? So let's do it. Let's figure out what the heat is, what amount of heat was dumped into this system. So our temperature is rising, and so we know that we're going to be somewhere in here on this graph because we've got liquid water where the temperature is rising. So we're right there. So we're going to use our equation Q is equal to mass times the specific heat of liquid water times delta T. So Q, I don't know why I'm writing a little q. I should be writing a big Q. Here we go, much better. So Q is equal to our mass of water, which is 450 grams. It should always be in grams, always, 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 times 4.184 joules per gram degree Celsius. times our change in temperature. And what is our change in temperature? It's 85 degrees Celsius minus 15 degrees Celsius. And fabulous! This problem gave us everything that we needed to know. So all we have to do is punch it into our calculator. 450 times 4.184 times the quantity, remember the parentheses, 85 minus 15. Unless you want to do that part in your head, you could just say 450 times 4.184 times 70, but otherwise, make sure that you have the parentheses right here, okay? And we should get that the heat is 1.32 times 10, 3, 4, 5 times 10 to the 5th joules. That's how much energy was put into this system. So what I have for you for the rest of the period is I have some practice problems for you for doing heat calculations. Hopefully some of it will seem fairly familiar, and the problem packet does have some guidance in it. So you're not all alone just watching one single video where Miss Fossbender does one single practice problem and then you have to do a million practice problems on your own. It's not true. The practice packet that you guys are getting is going to have some guidance there as well. So if you feel like you're getting stuck, just make sure that you're reading the directions and you're reading what's around it. Otherwise, I'll be back with you tomorrow and we can certainly talk about where you got stuck. Okay? So what we want for tomorrow is I want you guys to attempt these problems. You don't have to get final answers for them, but I want you to attempt to solve them. That way when I come in, I can help clarify things and I can help answer the questions that you guys need answers in order to be successful at this. Okay? So have a wonderful day. I think it's going to be great, and I'll see you tomorrow. All right?